In this video, I'm going to introduce you to a concept called logarithms. Before you watch this video, you might find it helpful to go back and review the rules for exponents that I started with in the lesson on exponential functions. The definition of the logarithm is stated for you at the top of the page. Take a moment and study this definition. The equation that I've circled here is an equation in what we call logarithmic form. And I can read it by saying log base b of m is equal to y. As I said in the rule here, this is equivalent to the equation that you see in exponential form here. Now let's look at the example in purple. In this problem, I gave you an equation in logarithmic form, and I'm going to change it to its equivalent exponential equation. I can write this equation in exponential form like you see here. If you have trouble seeing what I did, the colors here may help you. Note that the b changed to 3, the y changed to n plus 5, and the m changed to a. In this example, I gave you an equation in exponential form, and I'm going to change it to logarithmic form. I can do this by writing the answer you see here. If you have trouble seeing what I did, the colors here may help you. Note that the b changed to 5, the y changed to p plus 1, and the m changed to q minus 3. Also, I do need the parentheses here. If I had left the parentheses off, this would have said that the log only applied to the q. To work this example, I'll use the version of the definition of the logarithm in the parentheses at the top of the page. This version of the definition says that I need to ask myself, 2 to what power gives me 32? Pause the video while you see if you can figure this out. Because 2 to the 5th power is equal to 32, I can say that the log base 2 of 32 is equal to 5, and so I can say that the final answer to this question is 5. To work this example, I'll use the version of the definition of the logarithm and the parentheses at the top of the page again. This version of the definition says that I need to ask myself, 4 to what power gives me 1 over 16? Pause the video while you see if you can figure this out. Because 4 to the power of negative 2 is equal to 1 over 16, I can say that log base 4 of 1 over 16 is equal to negative 2. And so I can say that the final answer to this question is negative 2. If you have forgotten how to simplify an expression involving a negative exponent, you might find it helpful to go back and review the examples from the beginning of my video on exponential functions. Pause the video while you think about this question. For this question, I need to ask myself, 5 to what power gives me negative 5? Because it is not possible to raise 5 to a power that is a real number and get a negative number, I'll say that the correct answer to this question is no real solution. If you thought that the correct answer to this question was negative 1, note that 5 to the power of negative 1 is equal to 1/5, not negative 5. It might also help you to think about the graph of y equals 5 to the power of x. Recall that the value of y in this function can never equal 0, and it cannot equal a negative number. This should tell you that if a question asks you to take the log of a negative number or 0, the answer will be no real solution. To solve for x in the equation you see here, I will start by writing the equation in its exponential form. Next, I will note that 2 to the 3rd power is equal to 8, and then I can subtract 1 from both sides of the equation. As you can see, This gives me a solution of x equals 7. When you solve an equation that involves a logarithm, you should always check your answers by substituting them back into the original equation. If an equation involves a logarithm, it is possible for you to do all your math correctly, but get one or more answers that are not actually solutions to the original equation. So, to check this solution, I will substitute 7 for x in the original equation and find out if the two sides actually equal each other. As you can see, this gives me log base 2 of 8 is equal to 3. I'll talk about how you can use your calculator to type this in at the end of this lesson, so for now, I'll just note that I can change this equation to exponential form by writing 2 to the third power is equal to 8. Since that is a true statement, I can conclude that my answer of x equals 7 must be correct. To work this problem, I'll start by changing the equation to exponential form. For my next step, I'll use a formula for exponents that I discussed in the video on exponential functions. Recall that if we want to talk about an exponent in the form of a fraction, we want to talk about a root. You might find it helpful to go back and watch the examples at the beginning of my video on exponential functions. To cancel out the third power, I'll take the third root of both sides of the equation. To cancel out the fifth root, I'll raise both sides to the fifth power. That gives me an answer of b equals 32. As I said in the last example, you should always check your answers to any equations that involve logarithms by substituting the answer back into the original equation. In this case, since 32 to the power of 3/5 is equal to 8, I can say that my answer of b equals 32 must be correct. In most of the remaining examples in this section, I'm going to discuss some properties of logarithms, and the property you see at the top of the page is the first one I'm going to discuss. Generally, I don't want you to just trust me when I tell you that something is true. I'd much rather that you understand why it's true. That means that I'll start by showing you why this rule is a valid rule. I'm going to start by letting b and m represent numbers greater than 0, but b cannot equal 1. I'm going to let x equal log base b of m. I can write the last line in its exponential form by writing b to the power of x is equal to m. And then, since I said that x is equal to log base b of m, I can change the x from the last line to log base b of m. Since this gives us the rule at the top of the page, I can now say that this rule must be a valid rule. Now let's look at an example that uses this rule. In order to use this rule, both the large number that is being raised to the power and the base of the logarithm must match. In this case, both of these numbers are 4. That means that I can use the rule to say that this expression simplifies to x minus 5. Let's look at another rule. If b, m, and n are positive real numbers, and if b is not equal to 1, then I can say that m equals n if and only if log base b of m equals log base b of n. This means that if I start out knowing that m equals n, then I can put a log base b in front of both sides. And if I have an equation that says that a log base b of something is equal to log base b of something else, I can say that my two somethings must be equal to each other. To see why this is true, I'll start by writing a statement that meets the conditions of the problem. I'll let b, m, and n represent positive real numbers, where b is not equal to 1. I can use the rule that we just talked about to say that the equation m equals n is equivalent to m equals b to the power of log base b of n. Now I can look at this line as an equation in exponential form, and I can put this into the logarithmic form, as you see here. This gives us the result that we wanted, and so now I can conclude that this is a valid rule. In most of the examples in the rest of this lesson, I'm going to talk about the rules you see at the top of the page here. Take a moment and study these rules. To see why the first rule at the top of the page is a valid rule, I'll start by letting x and y represent real numbers, and b will represent a positive real number. I can define m and n so that b to the power of x is equal to m, and b to the power of y is equal to n. Since I cannot raise b to a power and get a number that is less than or equal to 0, this tells me that both m and n will be greater than 0. I can also change the statements that I wrote in exponential form into logarithmic form, as you see here. For my next step, I can take the equations that I wrote in exponential form in the last step, multiply the left sides together, multiply the right sides together, and set the results equal to each other. To multiply b to the power of x times b to the power of y, I can add the exponents and keep the bases the same. To see why this is the case, let's take a look at the note in gray. If you want to multiply x to the third by x to the second, you are saying that you want to multiply x times x times x by x times x. Since this means that you want to multiply 5 x's together, I can say that x to the third times x to the second is equal to x to the fifth. Take a moment, study this example, and notice how I can apply the thought process that I used in the example in gray to the equation in green. For my next step, I can use the rule I proved in the last example to put a log base b in front of both sides of the equation. Since log base b of b to the power of x plus y tells me that I need to ask myself, b to what power gives me b to the power of x plus y, I can say that log base b of b to the power of x plus y is equal to x plus y. And finally, since I started by letting x equal log base b of m and y equal log base b of n, I can substitute log base b of m for x and log base b of n for y. Since this gives us the equation that we wanted, I can say that the product rule is, in fact, a valid rule. To show that the quotient rule is a valid rule, I'll start by letting x and y represent real numbers, and b will represent a positive real number. Like I did in the last proof, I can define m and n so that b to the power of x is equal to m, and b to the power of y is equal to n. Since I cannot raise b to a power and get a number that is less than or equal to 0, this tells me that both m and n will be positive real numbers. I can also change the statements that I wrote in exponential form into logarithmic form, as you see here. For my next step, I'll divide the left sides of the equations I wrote in exponential form, divide the right sides of the equation I wrote in exponential form, and set them equal to each other. To simplify b to the power of x divided by b to the power of y, I can subtract the exponents and keep the base the same. To see why I say this, let's consider the expression x to the 7th divided by x to the 4th. Note that x to the 7th is equal to x multiplied by itself 7 times, and x to the 4th is equal to x multiplied by itself 4 times. Since I can reduce this fraction by canceling 4 x's from both the top and bottom of the fraction, I can say that x to the 7th divided by x to the 4th is equal to x to the power of 3. Take a moment, study this example, and notice how I can apply the thought process that I used in the example in gray to the equation in green. For my next step, I'll put a log base b in front of both sides of the equation. Since log base b of b to the power of x minus y tells me that I need to ask myself b to what power gives me b to the power of x minus y, I can say that log base b of b to the power of x minus y is equal to x minus y. And finally, since I started by letting x equal log base b of m and y equal log base b of n, I can substitute log base b of m for x and log base b of n for y. Since this gives me the equation that I wanted, I can say that the quotient rule is a valid rule. To prove that the power rule is a valid rule, I will start by defining my variables as you see here. For my next step, I will raise both sides of the equation from the last step to the power of p. To raise b to the x to the power of p, I can multiply my exponents. To see why I say this, let's consider the expression x squared raised to the power of 5. This is equal to x squared multiplied by itself 5 times. Since this gives us 5 groups of x's, with 2 x's in each group, I can say that I must have 10 x's multiplied together. Take a moment, study this example, and notice how I can apply the thought process that I used in this example to the equation in green. For my next step, I'll put a log base b in front of both sides of the equation. Since log base b of b to the power of px tells me to ask myself b to what power gives me b to the power of px, I can say that log base b of b to the power of px is equal to px. And finally, since I said earlier that x is equal to log base b of m, I can substitute log base b of m for x in the last equation. Since this gives me the equation that I wanted, I can say that this is, in fact, a valid rule. For my next example, I will start by using the product rule. Since 7x squared is equal to 7 multiplied by x squared, I can change the m in the product rule to 7, and I can change the n in this rule to x squared. Also note that I changed the b's to 5s. If you have trouble seeing what I did for this part of the problem, the colors here may help you. When they see this problem, many students think that they should start by using the power rule. However, as you see in brown here, if you try to use this rule, this would mean that you want to raise the entire 7x to the second power. And since the order of operations says that you only want to raise the x to the second power, that should tell you that you can't start by using the power rule here. For my second step in this example, I'll use the power rule to change the log base 5 of x squared to 2 multiplied by the log base 5 of x. If you have trouble seeing what I did, the colors here may help you. To work this next example, I'll start by using the quotient rule. Pause the video while you see if you can use this information to get this problem started. To use the quotient rule, you should be able to see that the b in the quotient rule changed to 3 for this problem. The m changed to 4x to the 5th, and the n changed to y. If you have trouble seeing what I did, the colors here may help you. For the next step in the problem, I can use the product rule because 4x to the power of 5 is equal to 4 multiplied by x to the 5th. For my third and final step in this problem, I can use the power rule to change the log base 3 of x to the power of 5 to 5 multiplied by log base 3 of x. In the last two examples, I started with a single logarithm, and then I used the product, quotient, and power rules to change it into an equivalent expression that involved a sum or difference of 2 or more simpler logarithms. In this example, I'm going to reverse the process. Because of the addition and subtraction signs in between the logs, I will use both the product and the quotient rules to work this problem eventually. However, I can't use either of those rules right now because neither of these rules tells us what we should do with the 7 in front of the log base 6 of a or the 4 in front of the log base 6 of c minus 1. This means that I'll start by using the power rule to change the 7 to a power of a. I will also use the power rule to change the 4 to a power of c minus 1. For my next step, I'll use the quotient rule because there is a subtraction sign between the log base 6 of a to the 7th and the log base 6 of q. Again, note that I'm reversing the process that I used in the last example. Note that my b's changed to 6's, my m changed to a to the 7th, and my n changed to q. For my third and final step in this problem, I'll note that there is an addition sign between the two logarithms. That means that I can use the product rule. Note that this rule says that I can combine the two logarithms into one logarithm by multiplying the a to the 7th over q by the quantity c minus 1 raised to the 4th power. For my next set of examples, I'm going to talk about two commonly used logarithms, the common log and the natural log. If the base of a logarithm is not stated, then we assume that the base is 10. This is called the common log. The second commonly used logarithm is the natural log. We abbreviate the natural log by writing ln, and it means that we want to talk about the log with a base of e. You might find it helpful to go back and review my discussion of e in my video on exponential functions. Now let's look at the example you see here. This example does not tell us a base that we should use, and so we must assume that we should use a base of 10. This means that I can change the equation into its exponential form as you see here. I can finish solving this equation by noting that 10 to the power of 4 is equal to 10,000, and then adding 3 to both sides of the equation. As I said earlier, whenever you want to solve an equation that involves a logarithm, you must always check the answer by substituting it back into the original equation and confirming that the two sides do actually equal each other. As I said earlier, I'll talk about how we can use our calculator at the end of this lesson, but you should be able to see that I can change the equation you see here into its equivalent exponential form by writing 10 to the power of 4 is equal to 10,000. Since this is, in fact, a true equation, I can say that my answer of x equals 10,003 that I found earlier must be correct. For my next example, I'm going to simplify the common log of 10 to the power of 14. I know that this is a log base 10, or what we call a common log, because, as I said earlier, we should assume that the base of a log is 10 if no base is stated. I'm going to work this problem by using two different thought processes, but I'll get the same answer using both methods. To work this problem using the method I'm going to call method number 1, I need to recall the definition of the logarithm, which is stated for you again here. Since we must assume that the base for this logarithm is 10, I can say that the problem is equivalent to the one you see here. That means that this question is telling me to ask myself, 10 to what power gives me 10 to the power of 14? Since the answer to this question is 14, I can conclude that the common log of 10 to the power of 14 is equal to 14. To work this problem using the method I'm going to call method number 2, I'll start by using the power rule to move the 14 out in front of the log so that it will get multiplied by the log of 10. To simplify this further, I'll note that the common log of 10 is equal to 1 because the log 10 that you see here should tell you to ask yourself, 10 to what power is equal to 10? Since the answer to that question is 1, I can change the log 10 to 1. Since the sign between the 14 and the 1 is a multiplication sign, I can say that the final answer to this question is 14. Note that this agrees with the answer I got when I worked this problem using the definition of the logarithm. To work this problem, I'll use the same two thought processes I used to work the last problem, and I'll get the same answer using both methods. I'll start by using the definition of the logarithm. I can use the second note at the top of the page to say that this problem is equal to log base e of e to the power of x plus 2. That means that I can use the definition of the logarithm to say that this question is telling me to ask myself, e to what power gives me e to the power of x plus 2? Since the answer to this question is x plus 2, I can say that the natural log of e to the power of x plus 2 is equal to x plus 2. I can also work this problem using the power rule. I can use this rule to say that the natural log of e to the power of x plus 2 is equal to the product of x plus 2 and the natural log of e. To simplify this further, I'll note that the natural log of e is equal to 1 because the natural log of e should tell you to ask yourself, e to what power is equal to e? Since the product of x plus 2 and 1 is equal to x plus 2, I can say that the final answer to this question is x plus 2. Note that this agrees with the answer that I found when I worked the problem using the definition of the logarithm. To work this example, I'll use the product, quotient, and power rules again. I do not want to start by using either the product or the quotient rule here because it's difficult to figure out what to do with the square root if I try to use either of those rules. If I want to take the square root of something, I can say that this is equivalent to raising that something to the power of 1/2. If you don't understand why I say this, I suggest that you go back and watch the beginning of my video on exponential functions. This means that I can use the power rule to say that this expression is equivalent to 1/2 multiplied by the common log of the quotient of 10x to the third and y. When they are learning this concept, many students prefer to write the answer you see in gray here. This is correct, but it's not the way a mathematician would normally write the answer. If you have trouble seeing what I did, the colors may help you here. For my next step, I'll use the quotient rule. Note that, because the 1/2 was multiplied by the log of everything in the previous step, I need to use parentheses to make sure that it continues to get multiplied by everything that it needs to get multiplied by. Like I said in the previous step, you can state the base of 10 if you want to, but it's not the way a mathematician would normally write the answer. Because 10x to the third is equal to 10 multiplied by x to the power of 3, I can use the product rule next. For my next step, I'll use the power rule to note that the common log of x to the third is equivalent to 3 multiplied by the common log of x. I'll also note that, because the common log of 10 tells you to ask yourself, 10 to what power gives me 10, I can simplify the log of 10 by writing 1. For my last step in this problem, I'll distribute the 1/2. In my last set of examples for this lesson, I'm going to talk about a formula called the change of base formula. If you use the button labeled log on most calculators, the calculator will assume that you want to use a base of 10. And, of course, if you use the button labeled ln on a calculator, the calculator will assume that you want to use a base of e. That means that, if you want to type a log with a base of, for example, 12 in your calculator, you may need to use this formula. Before I show you an example that illustrates how you can use this formula, I'll show you why it's true. As I said earlier, when I tell you that something is true, I usually do not want you to just trust me in the matter. I would prefer that you be able to verify what I say. I'll start by letting b and m represent real numbers greater than 0 such that b is not equal to 1, and I will define x by letting it equal the log base b of m. I can write this equation in its exponential form by writing b to the power of x is equal to m. For my next step, I'll note that we said earlier in this lesson that I can take the log of both sides of an equation as long as I use the same base on both sides. For this example, I'll use the common log, or log base 10. Now I can use the power rule to say that the common log of b to the power of x is equal to x multiplied by the log of b. Next, I'll divide both sides of the equation by the log of b. Since I defined x to be equal to the log base b of m, I can substitute log base b of m for x in the last equation. This proves the common log part of this formula is correct, and I can prove the natural log part in a similar manner. Now let's look at an example that uses this formula. In this example, I'll approximate log base 3 of 17 to 3 decimal places. I can use this formula to type this into a calculator using one of the methods you see here. If you're using a TI-83, make sure you close the parentheses after the 17. When you do this, you should find that the log base 3 of 17 is equal to approximately 2.579. Pause the video while you make sure that you can get this answer on your calculator. If you're using a TI-84, you don't have to use this formula. You can type alpha, then F2, which is above the window button, and then choose the log base option. If you have a TI-84, pause the video while you figure out how to use this option on your calculator, and make sure that you get the same answer I did. If you enjoyed this video, then please subscribe to our YouTube channel and see all of our products available at algebraforhomeschool.com.